Welcome to qnawire.
All right, so here we've been asked to give a test which will show the difference between reducing sugars and non-reducing sugars, and then a little bit about how we would know from that test whether we had a reducing or non-reducing sugar. Additionally, we've got some information uh, about sucrose and lactose, and we have to explain whether those are reducing sugars or not. So to begin with, one such test that can be used to tell the difference between reducing and non-reducing sugars is Tollens test. Tollens test, which uses Tollens reagent. G there. Tollens reagent is a mixture of silver nitrate along with ammonia and sodium hydroxide. Now, what Tollens test will do is that the silver ion, silver plus, which will be in solution, upon reacting with an aldehyde, will give silver solid. That is, the silver ion will be reduced to solid silver by the aldehyde. So the aldehyde acts as a reducing agent. That is, the aldehyde portion of a sugar is what makes it a reducing sugar. So this is a test. And the way you would recognize that this test showed evidence for a reducing sugar is that you would see the precipitation of solid silver out of solution. In fact, this is often deposited as a mirror-like silver substance on the inside of a test tube or beaker. Okay, so then let's continue with this question, which is also asking us about sucrose and lactose and whether or not they are, in fact, reducing sugars. Well, as we just talked about, for a sugar to be reducing, it must contain an aldehyde. The structure of an aldehyde is as follows. It's an R group carbon chain, double bond to oxygen, and a hydrogen. This is an aldehyde. Now, we often see sugars in a different form, not always their linear form. For example, here is sucrose. Well, it doesn't appear to contain an aldehyde, so we might expect then that this is not a reducing sugar. In contrast, we can look at lactose, which is a little big here. Let's shrink that down if we can. There we go. A more reasonable picture of lactose here. All right, we've got lactose and sucrose. If we just take a glance at these structures, neither one seems to contain an aldehyde. There's no double bonds to oxygen. Well, in fact, there's a bit of a trick to this that has to do with something called acetals, hemiacetals and acetals. So a hemiacetal has the form a carbon with a bond to an R group, a hydrogen, and an ether linkage, or an OR group. This is a hemiacetal. Hemiacetal. An acetal, in contrast, is a very similar compound, but instead of having an alcohol and an ether linkage, it simply has two ether linkages. This is an acetal, also known as a ketal. Now, the interesting thing is that acetals are in equilibrium with aldehydes. That is, acetals in solution will readily convert to aldehydes, and vice versa. In fact, they'll convert back and forth between aldehydes and hemiacetals, uh, eventually landing at some sort of equilibrium. Acetals, on the other hand, do not convert to aldehydes. So when we're looking at our sugars, lactose on the left here, lactose, and sucrose, oh, that's not how you spell sucrose, sucrose, we've got to look for more than just aldehydes, which would be useful in its linear form, but in the cyclic forms, we've got to look for hemiacetals, which we know can be converted into aldehydes. So we'll go through each of these sugars and see if they contain a hemiacetal. If they contain an acetal, that's fine. That won't convert to an aldehyde, and therefore the sugar won't be reducing. But if the sugar contains an acetal, we know that could convert to an aldehyde, which would make the sugar a reducing sugar. So we can just go through here carbon by carbon. This is not a hemiacetal because there's no OR linkages coming off this carbon. Same here, same here, same here. Oh, what about here? Now we've got an OR, right? Because this goes to oxygen, and then this is carbon, so that's like OR. And from here we can go to oxygen, and that oxygen goes to an R group. Well, that is an acetal, not a hemiacetal. Let's keep going. This carbon, no, no. What about here? Okay, this carbon has an OH. It's got an O, which is connected to a carbon, so it's got an OR, and it's got an H. This group right there is a hemiacetal. That means that lactose can be converted into a form which contains an aldehyde, and therefore lactose is reducing because it contains a hemiacetal or an aldehyde, depending on the form. What about sucrose? Well, I'll give you a hint. When it comes to searching these sugars, you can always look at these carbons because they're the only ones that are connected to oxygens that are connected to carbon groups. They're the only ones that contain OR groups. So let's look here. We've got carbon, oxygen, carbon, that's OR, carbon, oxygen, carbon, that's OR. That's an acetal, not a hemiacetal. Let's look at this carbon. Carbon, oxygen, carbon, that's an OR. Carbon, oxygen, carbon, that's another OR. That's an acetal, not a hemiacetal. This carbon has no ether linkages, neither does this one. This has an ether linkage, carbon, oxygen, carbon, that's an OR, but there's no OH. So sucrose does not contain any hemiacetals. Therefore, it cannot be converted into a form which contains an aldehyde, and it is not reducing.